Moving on to the next one, we have a go-kart traveling around the curved track as shown at a constant speed. And the first thing we want to do is draw the direction of the acceleration at 3 points, A, B, and C. Keeping in mind that it's moving at a constant speed, the only way for it to accelerate would be if it's turning. If it's moving at a constant speed, it can't speed up or slow down, so it has to be that changing directions acceleration. So at A, we are turning. We're going in a circle. The center of our circle is here, so our acceleration is inwards towards the center of the circle. At B, same thing. We're turning. The center of our circle is there, so our acceleration is also inwards because we're turning at that point too. For C, we aren't turning, we notice, and so because we're traveling at a constant speed and not turning, that means we are not accelerating, so our acceleration at C is just 0. We're now going to rank the magnitude of the acceleration in these situations. So we're going to keep in mind that while an object is going around in a circle, its acceleration is given by v squared over r. So looking at A and B, those are both situations where we're accelerating. Obviously C is the lowest because there is no acceleration. But between A and B, B has a smaller radius than A. They both have the same speed, so that top term is the same, but we're dividing by a smaller radius, which means the acceleration at B is greater than the acceleration at A, because A is a bigger radius, and they're both greater than C because C is an acceleration of 0. For our next one, we have an object swung around in a vertical circle at a constant speed, and we want to know if the tension in the rope at the top of the circle is greater than, less than, or equal to the tension at the bottom. So I'm first going to draw a free body diagram showing the forces acting on it at both the top and the bottom of my circle here. So at the top of the circle, I have the force of gravity going down, and I also have the force of tension from the rope going down. That's leading to that inward acceleration towards the center of my circle. At the bottom, I have the force of tension going up and the force of gravity going down, and I'm also accelerating inwards, but in this case that acceleration is up. So if I look at these forces here, I can see that at the top, Ft and Fg are working together to create that inward acceleration, whereas at the bottom, Ft has to oppose Fg and still add some additional force to create that inward acceleration. So that means this tension at the bottom is going to be bigger than the top. So to answer the question, the tension at the top is less than the tension at the bottom. And so the first thing I would say is at the top, both Ft and Fg combine to create that inward acceleration. And at the bottom, Fg opposes Ft. So that means that Ft must balance that force of gravity there and then create an inward acceleration on top of that. We're going to move on to some algebraic problems here. So up first we have a bicycle going around a track, a circular track with a radius of r, and we know the coefficient of static friction between the bike and the track is mu. The bike's going around at a constant speed, and we want to know the shortest time the bike can go around the track without slipping. So let's start with the free body diagram here. So once again, I'm going to take advantage of the side view, which is what we typically do when we have an object going in a horizontal circle here. And so in that case, we have the force of gravity going down on the object, the normal force going up, and I'm going to say it's traveling in a circle like this. Again, that velocity is coming out of the page. So that means the force of friction is the force keeping it moving in a circle, causing that inward acceleration towards the center of my circle here. So we're now going to go ahead and set up our max and our may. So in the x direction, we have the force of friction, and that's going to be equal to ma. Two substitutions I can make here. My force of friction I know is going to be at a maximum because we're riding around in the shortest amount of time. We're traveling as fast as possible around this track without slipping. So I can say that the force of friction is simply my coefficient of static friction times my normal force. I also can substitute in for my acceleration because I know that anytime I'm traveling in a circle, my acceleration is given by v squared over r. Setting up my y forces, I have Fn minus Fg, and that's going to be equal to 0 because we're not accelerating vertically. Okay, just horizontally. And so my normal force then is equal to Fg, which is simply mg. I can go ahead and substitute in for my normal force. I also know that my coefficient of friction, coefficient of static friction, is just given by mu. So I can say mu mg equals m times v squared over r. My m's will cancel out. And I ultimately want to get the shortest time that I can go around the track. So I'm going to first find the velocity of this object as it goes around the track. So solving for velocity, I get mu gr equals v squared. So the square root of mu gr is equal to my velocity. Now that I've solved for that velocity, I can use that velocity, and I know that when an object's traveling in a circle, its speed, or the magnitude of its velocity, is given by 2 pi r over t. So I can substitute in that velocity I just solved for, mu gr, for the velocity in this equation, and then I can go ahead and I can solve for t. So t is the time for one period, or the time to go around the track one time. And that's what I'm ultimately looking for. So I'm just going to rearrange this equation by cross multiplying first of all. So I get t times the square root of mu gr, and that's equal to 2 pi r. And then I go ahead and solve for t, and I get that t is the square root of mu gr over 2 pi r. Moving on to this next one, we have a situation where there's a puck sitting on a table, and the puck's going to be going around in a circle on a table that is frictionless. And it's connected to a rope with this hanging mass that's just remaining stationary. Okay, so puck's moving around in a circle where the mass is just hanging down and actually providing that tension to allow the puck to move around in a circle. So first thing I'm going to do, like I do with any of my force problems, is I'm going to set up a free body diagram, and in this case I'm going to set it up for both objects. We have two objects, so we're going to have two free body diagrams. So for the puck, we're going to have the normal force going up, the force of gravity going down. Once again, this is the side view here, so we're thinking about it traveling in a circle like that. And then we have, in this case, the force keep it moving in a circle is the force of tension going inwards, leading to that inward acceleration. For the other object, the hanging block, we're going to have the force of tension pulling up on it, and we're also going to have a force of gravity acting down on it. I'm going to call one of them Fg1 and the other Fg2 just to distinguish between the two. And this one we know is just remaining at rest, so its acceleration is 0. So this one's a little bit different than some of the system ones we did where they were accelerating together. Here they actually have two different accelerations because one's hanging at rest, the other's traveling in a circle accelerating inwards. I'm now going to go ahead and set up my F equals ma for each object. For the puck on the table, I really only care about my x forces. I could do my y, which would tell me that my normal force equals that force of gravity, but because we're not dealing with friction, that doesn't actually matter here. So I can just say that Ft, that force of tension, is equal to m, and I'm going to substitute in big M because that's what its mass is, times this acceleration, which is v squared over r. Okay. For the other one, for the hanging object, we're going to have Ft minus Fg2, and that's going to be equal to 0 because my acceleration is 0. So I can say that Ft is equal to little m, the mass of this object, times g. I can now go ahead and combine those two equations, so I can substitute in Ft into my equation for the puck, and I can just say little m times g equals big M times v squared over r. I'm ultimately looking for how fast the puck is traveling, so we want to find this velocity here. So I'm going to solve for that. So what I'm going to do is I'm going to first multiply both sides by r, so I'm going to have rmg, and then I'm going to divide by big M. So rmg over big M equals v squared, which means that v is the square root of that expression, rmg over big M. Moving on to this next one, we have a situation here where we have a bucket being swung around in a vertical circle attached to a rope of length L. So something like this would be the motion of the bucket. and here is our rope with a length of L, and we want to know what is the minimum speed the bucket must have at the top here so that the water doesn't fall out, similar to the demonstration that we did in class. So if we think for a second about the forces acting on the bucket, we're going to have the force of gravity going down on the bucket, of course. We're also going to have a force of tension from the rope going down on the bucket, and both of those lead to that inward acceleration that we have. When I go to set up my F equals ma here, I'm setting up my F equals ma in the y direction. I'm going to have Ft plus Fg is equal to m times v squared over r. And so we want to derive an expression for the velocity of the bucket, but we have a little bit of a problem here, and that is this force of tension. Okay, we don't really know anything about that force of tension. So we need to think about our concepts for a second. And we do have this hint here. When the speed is a minimum, what is the force on the rope? So as this bucket's being swung around in a vertical circle, imagine it going slower and slower and slower. What's going to happen to our forces? Well, gravity can't change. Gravity has to remain the same. But our total force has to get smaller because we're not traveling as fast. So what ends up happening? That force of tension gets smaller and smaller. We eventually hit this point where there is no tension. And if we had gone any slower, what would have happened would have been the rope would have had some slack in it. It would have looked something like this at the top of the circle, and it wouldn't have been a nice taut rope that's actually pulling on the bucket. In that case, the tension is 0. So at this point where we're going as slow as possible, there's this perfect speed where the force of tension does not actually act on the bucket itself. And only the force of gravity at the very top, that's the only force keeping it moving in a circle. And so once we get rid of that force of tension, we can make this substitution here, mg equals m times v squared over r. Our masses cancel out here, and we can solve for r in terms of L, the length of the rope, which is the radius of our circle, and fundamental constants. So I can just say g times the radius equals v squared. The radius is L, so g times L equals v squared, which means my velocity is the square root of g times L.